Hey, it's Dr. J. Today we're going to learn about the first derivative test. So last time we talked about partition numbers and critical values. So what we're going to do is we will start by making a list of the partition numbers and the critical values. Now recall, if the domain of the function is negative infinity to infinity, then these are the same. So we won't have to make two separate lists. So critical values and partition values. By the way, I use the word number and value interchangeably. So sometimes I'll say partition value, sometimes I'll say partition number. Critical value, critical number. A number and a value are, two different words that mean the same thing. So let's go ahead and start with some very straightforward examples where the domain is not restricted. So things like polynomials and exponential functions. Those will be graphs in which, and then odd roots as well. So things like cube roots and things like that. So polynomials, exponentials, and odd root functions. They have a domain of negative infinity to infinity, in which case we don't have to make two different lists. We can just make one list. Okay. So we'll start by finding the critical values. So let's take a very simple function, just a second degree polynomial. All right. So we'll start by finding the critical values. So we take the derivative. That's 4x plus 4. And we will set it equal to 0. Set it equal to 0. And solve for x. This one is super easy. I don't have to show all these steps, but since it's example 1, I will amuse you with the critical values. So there's only one critical value, which is also a partition number or a partition value. So this is what we call the first derivative test. It is sometimes referred to as a sign test. So we write out the x-axis. We don't worry about the y-axis. This is the x-axis. We place the partition numbers, the critical values, on the x-axis. I usually make a bin here. All right. Just sort of a partition. Yeah. If this is not actually a line, it's just to keep the two sides separate. So I don't want you to think that this is part of the graph or anything. So this is just a way of partitioning the segment. And then you pick a number in each bin. Yeah, so pick any number that you like over here, and then pick any number that you like here. These are what we call test values. or test numbers, whatever you want to call them. All right. And this is the first derivative test. So we are testing f prime of x, which is right here. All right, let's go ahead and do it. So pick any number that is on the right of -1. So 0. It's a good number to test. X equals 0. And then any number that's on the left of -1. So x equals -2. You pick the test values. There are any numbers that you like. All right, and then plug them into here, into the derivative. So that'll be 4 times -2 plus 4, which is -8 plus 4. And then all you care about is whether or not it's positive or negative. So this is positive. Oh, sorry. This is definitely not positive. This is negative. And so this test value tells you that the derivative is negative. And so that means the function is decreasing. The function is decreasing. Let's try the other side. So we're going to do f prime of, oh, by the way, this was f prime of -2. So now we're doing f prime of 0. 4 times 0 plus 4, 0 plus 4, 4. So that is positive. So that tells me the graph is increasing. Now, we're only testing one number. We have the critical value, -1. And so this tells us that the graph or the function is increasing on the interval -1 to infinity. And the function is decreasing on the interval -infinity to -1. Okay. So generally, if the sign of the derivative, that's why we call it a sign test, if the sign of the derivative at one test point in that interval is negative, then we say it's decreasing. Sometimes it's helpful to put -infinity on your number line here, and then put positive infinity on the number line here, and then you can see that the test interval goes all the way to infinity, unless there's another partition number, but we don't have that. We only have one critical value, so that's it. So that's the answer. Increasing and decreasing. So the first derivative test tells us that the graph is increasing or decreasing. Okay. Let's try another one. Example 2. So f of x is 5 times x minus 4 cubed. All right, so first let's find the critical values. Now, good thing we have the chain rule, because taking the derivative, we wouldn't want to have to cube this out and make a large expanded polynomial. I mean, we could if we wanted to, but with the chain rule, we don't have to do that. So we have 3 times 5 is 15, x minus 4 to the second, and then times the derivative of x minus 4, which is just 1. So the derivative is just 15 x minus 4 squared. Now we set this equal to 0. And solve for x. This one's pretty straightforward because it's already in factored form. You could probably just guess the answer. I will, for good measure, show all the steps. That was a lot of work. You probably could have just spotted it right here. Yeah, mental math. You got, as long as it's in factored form, it's pretty easy to see that if x is equal to 4, this entire factor becomes 0. So you could have just done it mentally, but just for the sake of mathematical, perfection and clarity, I'm showing all the steps. It's the kind of thing I'd like to see, on paper if I was grading your paper. I have experimented with having students, scan and upload paper documents, and it doesn't really affect the grade one way or another. So it's a lot of work and a lot of time. So I hope that you're, taking good notes and writing all this down, and the grade you're going to get is what you're going to get, and I don't need to see all that. Okay. So that's it. We have one critical value. So let's do the sign test. All right. I'm going to erase this. So let me go ahead and write my derivative up here. It's 15 x minus 4 squared. All right, so I've got infinity, I've got negative infinity, I've got 4, my critical value. I don't have to count out all the increments. I just put your critical value anywhere you like. It should be, in order, but since there's only one critical value, it's not that important. Just put it right in the middle. All right, so here's my bins. I'm making these 2 bins. All right, now above I usually do the derivative, and below I usually do the function itself. Although this is just a test, it doesn't really count as a graph. It's just giving me an idea of what the graph looks like. All right. So again, let's pick a test number over here, 5, 6, whatever you want to pick. All right, and over here, 1, 2, whatever you want to pick, 0. As long as it's to the left of 4. All right, you get to pick these numbers. And then you plug them into the derivative. So you got f prime of 6 is 15 times 6 minus 4 squared, which is 15 times 2 squared. Now remember, I don't actually care what number it is. I just care whether it's positive or negative. So you don't have to, especially when these problems start getting more complicated, I don't want you spending a bunch of time calculating what that is, right? It's 60 if you actually care. But, at some point you can just go, I don't care what it is, because the numbers might start to get up into the hundreds and the thousands, and I really don't need you spending a lot of time calculating it. Okay. So that tells me that the graph is decreasing. It's going down. All right. Oh, why did I say decreasing? Oh. I'm looking right at it. I was just testing you. See if you're paying attention. Increasing. Positive. Maybe I was thinking about this side. Let's see. All right, so now we have f prime of 1. So the same function, 15 times 1 minus 4 squared, 15 times negative 3 squared. That's still positive. So it is still increasing. Yeah. Negative 3 squared is 9. 9 times 15 is whatever it is. I don't care what it is. It's 135 if you care. I think. 9 times 15 is 135. But again, I don't care. All I care about is the sign, whether it's positive or negative. So this graph is always increasing. Yeah, decreasing DNE does not exist. It's never decreasing. What's happening at 4? It's neither. It's neither increasing nor decreasing, but we will include it in our answer. We'll say that this function is always increasing. Basically, the graph looks like this. So it has a slight bend at 4. This is the point 4, 0. We'll talk about this later in the second derivative. So since we're only doing the first derivative, I can't really talk too much about what's happening at 4 right now. But I will say that it is still increasing at that point. It does sort of have a momentary pause, because the derivative was equal to 0. So you could maybe kind of draw it like this, but then it's still increasing. Okay, let's do another one. We're going to keep doing this test until we talk a little bit more about the second derivative in my next part. So this is really just the first derivative test. So we have f of x is negative 4 times x plus 5 to the 2/3. Remember what 2/3 means. It means the cube root of x plus 5 squared. I'm not actually going to write it that way, but it is useful to maybe think about it that way. This is an odd root function. So we don't have to worry about asymptotes or holes or points where the derivative doesn't exist, or points where the function doesn't exist. There might be a point where the derivative doesn't exist. Let's find that out right now. F prime of x is negative 4 times 2/3 times x plus 5 to the negative 1/3, and then times 1. Yeah, the derivative of x plus 5 is just 1. So this is negative 8/3 times x plus 5 to the negative 1/3, which is negative 8 over 3 times x plus 5 to the 1/3. So when we set f prime of x equal to 0, you get no solution. Since negative 8 does not equal 0. Yeah. There's no variable in the numerator. So when you set a function or a derivative or any equation equal to 0, you are setting the numerator equal to 0. But remember, there's two types of critical values. There's the type where the derivative is equal to 0, and that never happens. So look for x where the derivative does not exist. In other words, set the denominator equal to 0. So 3 times the cube root of x plus 5 is equal to 0. You don't have to do all the work. You could just clearly say that it's going to be negative 5. I have a hard time doing that. I always want to show the steps. So it's the cube root of x plus 5 is equal to 0. So x plus 5 is equal to 0. You cube both sides. Yeah. And then that cancels the cube root. This one's a little messy because it has a little 3 as the index, and then it has a big 3 as the coefficient. I already divided off the big 3, and that gave me 0 still. 0 divided by 3 is still 0. Then I came up here and I cubed both sides, but when you cube 0, you still get 0. And then you subtract 5 and you get x equals negative 5. So you only have one critical value. So your function is negative 8 over 3 times the cube root of x plus 5. You only have one critical value. X equals negative 5. So when we do our sign test, again, there's only one critical value, so I'm just partitioning it at negative 5. Those are the two bins. Pick a test value on the right. Usually, if I can get away with it, if it's possible, I usually pick 0. It's a very easy number to pick. And then I'm going to go with negative 6 on this side. Again, you get to pick any number you like. And now we plug it into the derivative. So f prime of negative 6 is negative 8 . over 3 times the cube root of -6 plus 5, which is -1. Well, that's going to be positive because the cube root of if this was a square root, I'd have a problem here. You can't have the square root of -1, not in this class. I mean, it would be an imaginary number, and we're not discussing those in business calculus. Not until somebody finds a use for them, we won't be studying them in this class. They are used in science and engineering and physics and some other areas, but not in social sciences and business calculus. Okay, so that's a positive number. It's a -8 divided by -3, if you really want to know what that comes out to be. The cube root of -1 is -1 times 3, but I don't care. It's a negative divided by a negative, so it's a positive. So over here, f of 0 is -8 over 3 times the cube root of 5. And again, you don't have to put this into your calculator. You don't care what it is. All you care is that it's negative. So this side is going to be decreasing, and this side is going to be increasing. All right. I should make a point. Be careful with arrows. I almost screwed this up earlier. I went like this. This is still decreasing. All right. And so you have to be careful with arrows, right? It looks like this arrow is going up, right? But you want to read it from right to left, from left to right, sorry. Read from left to right. So as you move from left to right, this graph is actually going down. So this arrow is very misleading. You want to think about it as if it were going from left to right. So that is decreasing. Right. Similarly, something like this. Yeah. Doesn't that look like it's decreasing? But it's not. It's increasing. Or we call it an interval of increase. I say it both ways. Interval of increase or increasing. I know it's confusing, right? Because doesn't it look like it's going down? But you always want to read from left to right. So this arrow is actually going this way. Don't change the line. Yeah, the line is still going in the same direction. And doesn't it now look more like it's increasing? So you have to be really careful with arrows. So decreasing means going down as you read from left to right. Increasing means going up as you read from left to right. So this function is interval of increase is -∞ to -5. Interval of decrease is -5 to infinity. And we never put a bracket at the critical value. It's always an open parenthesis because technically at that point it's neither. It's neither increasing nor decreasing. And then if for some reason they both come out to be negative, or if they both come out to be positive, then you ignore the critical value entirely and you just go right across from negative infinity to infinity, as if that critical value never happened. All right, until we get to the second derivative, and I'll show you what to do in that case. But we're not ready for that yet, so we only have one test. So this test only matters when they give you two different values, positive negative or negative positive. They give you the same value. It's almost like the test. I wouldn't say it's inconclusive. It's not inconclusive. You still get an answer, but it doesn't tell you anything about the critical value. We need another test to then resolve that issue, which will come later. All right. Let's keep on rolling. Let's do one more of these, and then we'll start talking more about the graph. This doesn't really tell you what the graph is. It just tells you the general shape. So I know to the left of -5, the graph is going up, and then to the right of -5, the graph is going down. But that's all. That's all this test tells you. Let's do one more. Kind of going through one of each type here. So let's do, this is one we did yesterday. It's not exactly the same, but it's in the same family as one we did last time. 3x squared times e to the -16x. It's the family of exponential functions. So let's find the derivative. Now we have a product. So I like to put the dot to remind me of the two separate functions that I'm using the product rule. So the derivative of the first is 6x times the second plus the derivative of the first, 3x squared times the derivative of the second, which would be e to the -16x times -16. Remember that chain rule. I was using the chain rule in one of the other examples, but it ended up being multiplied by 1, right? And that's why I did that. Even though I know that multiplying by 1 doesn't change the answer, it's a good habit to get into for an example like this. If that is not 1, then you need to make sure it's there. So I've got 6x e to the -16x minus 48x squared e to the -16x. I'm going to factor out the e to the -16x, and I'm going to set this equal to 0. All right, I'm trying to find critical values. So I'm setting my derivative equal to 0. I talked about this last time. I'm not going to make a big deal about it this time. An exponential function cannot equal 0. All right. Talked about the whole logarithm. I went off on a side lesson on what the logarithm does to 0, and it's a non-existent. It gives you an error on your calculator. So there's an asymptote there, and so we're ignoring that. Yeah, there's an asymptote in the logarithm function, so this gives you no solution. So that means we can just solve this one. Let's factor out a 6x. Yeah, those are both divisible by 6. Split this up. 6x is equal to 0, or 1 minus 8x is equal to 0. This one's pretty easy. Just divide by 6. You get 0, or 1/8. I didn't show any steps there, but I guess I will. Whenever I skip steps, I feel like I'm leaving the door open for confusion. So I'm subtracting 1 from both sides, dividing by -8. What's nice about showing the steps is it prevents any kind of sign errors. So check, you can see that I had it right. If there was a sign error, suppose I put it as -1/8, then by showing the steps, it clarifies that either I made a mistake or in this case that I didn't make a mistake. So those are my 2 critical values. Let's take, now I remember, ignore this, but don't forget about it. It's still there. So I've got 6x times 1 minus 8x times e to the -16x. That's my f prime. My critical values are x equals 0 and 1/8. So in my sign test, I've got 2 bins. And again, this is not a perfect representation of the graph. This is a test representation. Just gives you an idea. So I don't have to put 1/8 very close to 0, right? In reality, if I busted out, my graph paper, which at some point I might break this out and start drawing these graphs with more detail, then the 1/8 would be very, very close to 0. But you don't want to do that here. You want to give yourself some space to work here. All right. So let's go ahead and test some test values. We're going to have to pick one in each bin or in each region. So this is kind of tough here. You're going to have to pick something between 0 and 1/8. So let's do 1/16. Yeah. Halfway between the two. Something larger than 1/8. How about 1? And something less than 0. How about -1? Okay. And then let's plug it into the derivative. I'll start over here. So I've got 6 times 1 times 1 minus 8 times 1. Might as well show it. Then e to the -16 times 1. 6 times 1 is a positive number. 1 minus 8 is a negative number. E to the -16 is still a positive number. If you're not sure, use the calculator. If you don't believe me. The power will be negative, but when you raise a number to a negative power, you don't get a negative number. You get a very small number. So it is a very small number. All right, and I'm not using my calculator unless I absolutely have to. But I know, I've done it before, and if you don't believe me, plug it into your calculator, and you will get 0.00000, whatever it is. I don't know exactly how many zeros it has, but it is a very small positive number. So overall, we have a positive times a negative times a positive, and so this region is negative. This is getting tricky now. Right? The first few examples were pretty straightforward. This one you have to pay very close attention. All right, let's try 1/16. So we got 6 times 1/16. 1 minus 8 times 1/16. E to the -16 times 1/16. All right, again, I don't care what this is. 6 times 1/16 is a positive number. 8 times 1/16 is 1/2. 1 minus 1/2 is a positive number. And then e to the -1, right? This power would be -1, is still a positive number. So altogether, this region is positive. By the way, everything I'm writing in red here, if you have good mental math skills, you can just look right here, mentally figure out what those values are. Remember, you don't care what the numeric value is. You just care about whether they're plus or minus, and then you can jump right to what I'm writing in black. So what I'm writing in black is sort of the minimum amount of writing that you would need to do. I'm writing every little thing that I say and everything that I think. I'm writing it all out in red. All right, so now I've got -1. So I've got 6 times -1 times 1 minus 8 times -1. E to the -16 times -1. All right, 6 times -1, that's negative. 1 minus minus, that's double negative, that's going to be positive. And then E, that's double negative, so that's 16. E to the 16 is still positive. In fact, you can really just ignore the E part because this is going to always be positive. Just the E part is always positive. See? The last sign in all of these tests are always positive. So this one, negative, is the winner. Okay. So altogether, these three signs all together come out to be negative. All right, so now we got an idea of what the shape looks like. Be careful with your arrows. So decreasing means going down to the right. Or you can write it this way. That's still decreasing. So I wouldn't do that, but you could. It wouldn't be wrong. I like to see the arrow going down. It makes your brain think that it's going down, right? And then this one's increasing. Yeah. And then this one's decreasing again. Okay. But again, if you wrote the arrows the other way, this confuses the heck out of a lot of my students, but it's true, that is still decreasing. It would just be as if you were riding the roller coaster backwards. So I'm going to ride the roller coaster forwards, which is from left to right. So it is decreasing on the interval -infinity to 0, open, union 1/8 to infinity. And it is increasing on the interval 0 to 1/8. Okay, so that is your lesson on increasing and decreasing intervals. So the next thing we're going to talk about is what happens when it changes from increasing to decreasing. These are called relative or local extremes or extrema. Extrema means extreme values. We call those extrema. So, if f prime of c is equal to 0, and f prime of x is less than 0 when x is less than c, and f prime of x is greater than 0 when x is greater than c, then f of c is called a relative or local minimum. Occurring at x equals c. All right. In other words, when you do the concavity test, all right, c is a critical value. Yeah. Because the derivative is 0. F prime of x is less than 0 when x is less than c. That means that this side is negative. F prime of x is greater than 0 when x is greater than c. That means this side is positive. So this is just a formal written explanation for the sign test. This is what it will look like when you do the sign test, or the first derivative test results. Then it's called a relative minimum. And you can kind of see why. Look, the graph is going down. Yeah. And then it's turning around and coming up. I will point out that this is a y value. And we sometimes call it y min. Yeah. Just to indicate that it is the minimum y value. Because it's a function, we call it f parentheses c, but in your mind, it is a y value on the graph. And then it occurs at this critical value. All right. It essentially looks like this. And the point is x equals c, y min equals f of c. So this is where that point occurs at. If I was graphing it, this would be my x value, and then this would be my y value. If I was graphing. We're not quite ready to draw detailed graphs yet. I mean, we could for a very simple parabola or something. Maybe I'll have you graph a parabola. Let's do something a little bit more exciting than a parabola. I got to tell you what a maximum is. Yeah. If f prime of c is equal to 0, just switch these. Change this to negative. Change this to positive. So I actually don't recommend memorizing both of them. Just memorize one. So if it goes from negative to positive, then that means it's a min. Well, then you don't have to memorize the other one. If it goes from positive to negative, it's a max. I will write it down for your notes. The derivative has to be 0. That's what gives it the critical nature. Yeah. And f prime of x is greater than 0 when x is less than c. That's this one. And f prime of x is less than 0 when x is greater than c. That's this side. It's the right side. Then f of c is a relative, also known as local, maximum occurring at x equals c. And then the notation that we would use for this point is y max. Y max. And it would look like this. And the point would be x equals c, and y max is f of c. So that would be your x and your y. Actually, I want to write it the other way. I like to put x here. So that's the x value. Yeah. And then y up here. It doesn't really matter, but I feel if it's a maximum, it should be above, it looks like it's, I'm labeling it like, a little indication. It doesn't really matter anyway, as long as you, it matters in so much that you need to be able to answer the question correctly. So if the graph is going from increasing on the left to decreasing on the right, then we say that that is a local or a relative max. All right, well, now that we have the definition of local maximum and local minimum, and we have the first derivative test, we can explore the shape of the graph in more detail. We can find relative, also known as local maximums and minimums, or extreme values, and sort of start piecing together what the shape of the graph looks like using calculus. So let's first find the critical values. So we take the derivative, we get 12x squared plus 24x. We set this equal to 0 and solve for x. This is a pretty simple equation. They are going to get worse. If the equations are more complicated, you might need some more sophisticated methods, formulas, recipes, more complicated factoring procedures. But this one's pretty straightforward. They both have a common factor of 12 and an x, so I can pull that out. You can hopefully solve these just with mental math. So you're going to get 0 and -2. When you list them as critical values, I don't care what order they're in, but when you go to do the sign test, or what's also known as the first derivative test, I do care. Now, I won't actually see you perform the test, but I will see the results of your test in your answers. So make sure that they're in the right order when you perform the test, which really is the reason why I was encouraging you earlier in the lessons to just put them in order to begin with. Now remember, it's a sign test. So you can use the original function or this. Yeah, so you can use the original or you can use the factored version. They're both going to give you the same results. You only care about the sign. You don't really have to spend a lot of time calculating what the answer is. So let's pick a number larger than 1. Larger than 0, such as 1. And then plug it into here. I choose this one. 12 times 1 and 1 plus 2. And all you care about is whether that's positive or negative. So 12 times 1 is positive. 1 plus 2 is positive. When you multiply two positives, you get a positive. Now pick a number between -2 and 0, like -1, and plug it into here. -12 times -1 is negative. -1 plus 2 is positive. You have a negative times a positive, so that's going to be negative. Finally, pick a test value over here, -3. Plug it in. 12 times -3. -3 plus 2. 12 times -3 is negative. And again, I don't care what it is. It's -36, but I just care that it's negative. -3 plus 2 is also negative. So there's a negative times a negative, so that's going to be positive. So the graph is increasing until you get to -2. Then it's decreasing until you get to 0. And then it's increasing again all the way to infinity. And so that means that -2 is a max and 0 is a min. Now, I want to make it very clear, -2 is where the max occurs. It's not the actual maximum. And same with 0. 0 is where the minimum occurs. Right? Now, I don't know what the actual maximums and minimums are. I'm going to have to plug them in. So I have to, right here, f of -2, I don't know what that is yet. And f of 0, I don't know what that is yet either. But I have my f right here. So f of 0, that's the easiest one. That's just -20. So we say a local maximum, or you could say relative, of, oh, by the way, why did I say maximum? I meant 0. It's a minimum. Of -20 occurs at x equals 0. Now let's do f of -2. That's going to be the maximum. Very important that you reference your test as you're going along. I almost screwed that one up. Let's do -2. So I got 4 times -2 cubed plus 12 times -2 squared minus 20. 4 times -8 plus 12 times +4 minus 20. -32 plus 48 minus 20. -4. Yeah. -32 plus 48 is... oh, wait a minute. No, not -4. -32 plus 48 is 16. 16 minus 20. Oh, it is -4. Just making sure. So a local, I should have my calculator out, but I'm trying to do it just with mental math. I might have to break it out in a little while. I just heard my phone ring, so I know it's nearby. A local maximum of -4 occurs at x equals -2. Now be careful. The actual minimum, we call that y min, is the y value, -20. And the actual maximum, we call that y max, is the y value that is the actual maximum. Now it's called a local maximum because it's within a neighborhood, in that general region or in that area, this is the highest point. It doesn't mean it's the largest point in the entire graph. It just means it's the largest in that area. And then we have the increasing. On the interval or intervals -infinity to -2, union 0 to infinity. So those were the two that were going up. I should have wrote this down earlier. My test had it said ink and deek. So this is the formal way to write those answers or those results. It was decreasing only in the middle, in that middle section. I just erased the entire test results, but this is how you'll summarize those test results. Okay. At some point, I'll bust out the graph grid and draw a more detailed graph, but generally what it looks like is this. That's sort of a very loose interpretation of what it looks like. So it's increasing, and then it's decreasing, and then it's increasing, and then it has a maximum here. That's this one. -2, -4. That's this point here. And then it has a minimum. 0, -20. That's about as good as I could do without actually, using the grid. Just a rough idea of what's going on. All right, well, we got a lot more to do today, so let's do another example. I'm kind of just going to go higher and higher and higher. Let's do a quartic. So this is called a cubic, third power. Let's do okay, so the next one is a quartic. Fourth degree polynomial function. Call this one g of x. X to the fourth plus 22x to the third minus 54x squared plus 31. So find the critical values, the intervals of increase and decrease. I'm going to say ink and deek. And the x values where local extrema occur. Mainly because of time. This video has gone on pretty long already, and I don't want to have it take longer than necessary. Once you have the x values, some of the questions might also ask for the y value, in which case you would just plug it in. But this is a pretty, gnarly function. And so just to make our lives a little bit easier, we'll skip that step and we'll just find the x values. All right, everything starts with the CVs, the critical values. So we'll take the derivative. That's 4x cubed plus 66x squared minus 108x And then plus 0, the derivative of 31 is 0. Generally, we just don't write that. And then we set the derivative equal to 0 and solve for x. So we've got 4x cubed plus 66x squared minus 108x equals 0. We're going to factor out as much as we can. I think 2 is as good as it gets. Oh, and x. So all of these factors are divisible by 2, and they all have at least one x. I was hoping I could take out a 4, but 66 is not divisible by 4. So get 2x squared plus 33x minus 54. Keep on factoring. I'll give it a couple minutes, maybe, I'll give it like 30 seconds. You should give it a minute or two. If you can't figure out what the factors are within a couple minutes, then use another technique, right? Use a device or a formula or God forbid, guess or Google it or something. I'm going to try to do it with my brain. So remember how you factor. You ignore the outside factor, 2x, and you ignore the middle factor, the 33. And you just look at the first and the last factor. So 2x squared, that's not too hard to guess. 2x times x is 2x squared. Now 54, I don't know, it's 9 times 6. But that's not the only possibility, right? So now I'm going to peek and see if the middle number comes out to be 33. All right. Does it? 2 times 9 is 18. Yeah. And 6 times 1 is 6x. There's no way that that's going to be 33. Yeah. It's impossible. So that means 6 and 9 aren't going to work. You could try 9 and 6. Try just the other way. 2 times 6 would be 12. And then 9 times 1x would be 9. It's still not equal to 33. So we're looking right here to see if it's possible. So that means 9 and 6 are not the correct factors. All right, I'm going to give it one more try. 18 and 3 also make 54. 18 times 3. So 2 times 18 is 2x times 18 is 36x. And then 3 times x is 3x. Yes, 36 minus 3. So I just have to make that one plus and that one minus. So make the 3 a minus. And then it'll be 36 positive, and then negative 3x will be positive 33x. So there you go. That's factoring in a nutshell. That's called the guess and check method. All right. If that doesn't work, you can always use the quadratic formula. All right. Again, on a test, if this was a timed exam, I wouldn't waste 5 minutes guessing. I would spend 30 seconds or a minute. And even if you have to set a little clock to kind of budget your time. After that, use some technology or use a formula or do some other thing to find those factors. All right, so you're going to get 3 critical values. X equals 0, x equals 3 over 2 or 3 halves, and x equals negative 18. So those are our critical values. Again, here the order doesn't matter, but when I do my test, the order is going to matter. So now we're going to do the first derivative test. Negative infinity, positive infinity. I got to put them in order. So negative 18 0 and 3/2. Now remember, this is called the first derivative test because you're testing G prime and all you care about is whether the sign is positive or negative. That's all you care about. You can use any of these versions of the derivative. I usually go with the last and final one because that's going to be the simplest one to test. Just going to copy it right here. Okay. I got my critical values listed out in order. Now I'm going to pick some test points. Any number greater than 1.5. So how about 2? Remember, this is an x value. Yeah. So you could say x equals 2 as well. Either way, or you can just say 2. Something between 0 and 1.5. X equals 1. I like to say x equals because it reminds you that you're plugging it into here. But again, it's an x-axis, so everything on this test is an x. How about something between 0 and -18? You don't have to go too far. -1 will be fine, but you have lots of choices. And then something way over here, -19. All right, so these are your test values. I like to partition, that's why we call them partition numbers as well, into bins or regions that I'm testing. Just sort of keeps these things from contaminating each other. All right, so this is what we're testing right here. So let's take 2 and plug it in here, here, and here. All right, now all I care about is whether it's positive or negative. That's all I care about. I don't care about the number that it comes out to be. All right. Now, you might care if you wanted to know the slope, because remember, G prime is telling you the slope. But in this lesson, I mean, that was the last chapter where I was really concerned with the slope. It's not that it's not important anymore, but it's just not as important anymore. So let's move on. If I plug in 2 into here, that's going to be positive. First factor. The next factor, if you plug in 2, that will also be positive. 2 times 2 is 4, minus 3 is positive. And if I plug 2 into here, it's positive. So altogether, positive times a positive times a positive, that bin or that region is positive. Now we go to my next one. 1. 2 times 1. That's positive. 2 times 1 minus 3. That's negative. 2 times 1 minus 3 is negative. And then 1 plus 18 is positive. So I've got positive, negative, positive, which comes out to be negative. And just keep going. If you want to guess, once you get the first couple, you can just kind of see a pattern. I bet you the next one is positive, and I bet you the last one is negative. But notice I said bet. You are essentially gambling. There are examples that go positive, negative, positive, positive, right? There are examples that go positive, negative, negative, negative. Any combination of pluses and minuses is possible. Now, the most likely is alternating, plus, minus, plus, minus. That's the most likely combination. Or minus, plus, minus, plus. But it's not the only one. There are other possibilities. So you probably should still check, okay? Let's try the next one. Let's try -1. That'll be negative. 2 times -1. That'll be negative. 2 times -1 minus 3. Still negative. And then the last one would be positive. -1 plus 18 is positive. So you have 2 negatives and 1 positive. So my guess was right. And then finally, let's guess 19. Let's plug 19 into these things, or sorry, negative 19. That's important. 2 times negative 19 is going to be negative. 2 times negative 19 minus 3 is negative. And then negative 19 plus 18 is negative. Negative times a negative times a negative is still negative. So that is the first derivative test. So here are the results. The results are decreasing, negative 19. So I tested, I got a negative, so it's decreasing. I tested, I got a positive, so it's increasing. I tested, I got a negative, so it's decreasing. I tested, I got a positive, so it's increasing. If it's changing from negative to positive, it's called a min. Now, the min is not 18. The min is at negative 18. And then this is a max. And again, the max is not 0. The max is at 0. If you want to know what the actual maximum is, you have to go back to the original problem and plug it in to find out the y value. I've already erased it and I'm moving on. And then min at x equals 1.5 or 3/2. So we have increasing. That'll be negative 18 to 0 union 3/2 to infinity. That's these two up. Decreasing. Well, the opposite of that. So negative infinity to negative 18 union 0 to 3/2. Relative or local min at x equals negative 18 and I'm putting a comma 3/2 relative max at x equals 0. All right. And then I'm not going to find the y values. If you are curious, you want to know what they are. The 0 one's the easiest one. It would be 31, even though I already erased it. If you remember, if you plug in 0, you just get the last term in the original function. So that would actually be easy to do. These ones, they're not impossible. It's just, it would take me 10 minutes, and I just want to move on to the next example. All right, so notice I go second degree, third degree, fourth degree. What's next? Fifth degree polynomial for the next example. It's called a quintic. So negative 4x to the 5th plus 50x to the 4th minus 160 x to the 3rd plus 15. Same process. Just get right into it. Take the derivative and find the critical values. So I got negative 20 x to the 4th plus 200 x to the 3rd minus 480 x squared, and then the constant becomes 0. Most of these problems are prefabricated by me so that you don't have to suffer too bad. So I kind of make them so that they might look scary to the untrained eye, but once you dive into it, you'll see that they should be pretty easy to solve. Notice that these are all divisible by 20, And you can pull out two x's. You can pull out an x squared. So that really makes the problem a lot easier. You do have to be careful with signs. When you pull out a negative, it changes the other signs. And you're removing the x squared, so that lowers the powers of the remaining terms. And then you're going to set that equal to 0. Wow, it just got really dark. All right. So again, prefabricated. This one's a little bit easier than the last one. Ignore the negative 20x squared and then factor the remaining factors. It's super easy when the leading term is just x squared. It's just xx. And then two numbers that multiply to be 24. So you could try 12 and 2. Right? But then they have to add to be negative 10. So notice that wouldn't work, right? If they're both negative, you get 24, but you don't get 10. If they're both positive, you won't get a negative 10. So try 6 and 4 instead. Maybe that was your first guess anyway, and I'm just playing the fool to see what it would be like to guess wrong, right? Guessing correctly. So that's it. Those are your factors. And then you get your critical values. This one, x squared. The only number that makes this 0 is 0 itself. All right. What number makes this 0? 4, clearly. And then this one, 6. Hey, look, they're already in order for me. That's very nice and convenient. All right, 0 is going to go way over here. Maybe not way over there. It's a little bit too far. How about right about there? 0, 4, and 6. So here's what I'm going to test. You can test any one of these. You can use the original. Don't use the original function, though. So if you're going to test, these are your options. Anything from the derivative, any of these are all equivalent. All right. If you tested the original function, it wouldn't tell you whether it's increasing or decreasing. It does tell you something, the original function, but it doesn't tell you what I'm asking. The original function just tells you where the maximum or the minimum y values are. That's pretty much all you use the original for. Pretty much. I mean, there's other things we can use it for, but that's not in this lesson. All right, let's pick some test values. I just go with the most basic ones: -1, 1, 5, and 7. I mean, you are allowed to pick any number you want, but there's no reason to, rack your brain over it. Just plug it in and see. All right, let's do it. Let's try to do this one mental. Totally mental. All right, see if you can follow along with me. -1, square it, positive, times -20, negative. All right. -1 minus 4, negative. -1 minus 6, negative. So altogether, 3 negatives make a negative. Now, if I wanted to take a risk, do you bet? Or would you bet? That's a question. Would you bet on it? Once you get the first one, you can say, well, the most likely thing is that it's just going to alternate like that. Well, I don't know. Well, I don't trust it. Let's see. Let's test it. Let's see. So let's try 1. Plug it in here. 1 squared, that's positive, times -20, that's negative. 1 minus 4, that's negative. 1 minus 6, That's negative. I'm glad I didn't bet because this is not positive. That's still negative. Okay, so that means 0, although it is a critical value, it is not a maximum and it's not a minimum because the sign of the derivative is not changing. All right. Let's try the next one. 5. 5 squared. That's positive, right? 5 squared is 25. Times negative 20. That's still negative. Notice that negative 20 is going to make that first one negative every time. 5 minus 4, that's positive. 5 minus 6 is negative. I have a negative times a positive times a negative. That is positive. So we got one. Yeah. That is a min at x equals 4. And again, the min is at x equals 4. It's not the same thing as saying the min is x equals 4. Now I would probably bet that the last one's negative. Would you bet? I would. But I'm still going to test. So now plug in 7. 7 squared is 49, positive, times negative 20. There it is again. That first factor is negative. Here's why I like to put the bin walls up to keep these guys from contaminating each other. 7 minus 4, that's positive. And 7 minus 6 is positive. A negative times a positive is in fact negative. So that one is decreasing. And so I have a max at x equals 6. All right, and this is neither. So we're just going to ignore this because it does not change. It doesn't mean that that point vanishes from its existence. It just means it's not a turning point. It's not a local max or a local min. The graph is not changing its direction at that point. It's still on the graph. It might be handled in the next derivative test that we learn. Today we really only have one test. So, all right, so let's summarize our results. We have decreasing, negative infinity all the way to 4. Yeah, you just ignore that 0. You go right over it like it never happened. All right. It's like a bump in the road, but it's still decreasing. Oh, and then again from 6 to infinity, decreasing. And then increasing just between 4 and 6. And then we have a local or relative max at x equals 6. And we have a local or relative min at x equals 4. Again, if you're curious, the y values, I'll say DIY, do it yourself. Take these x's one at a time, of course, plug them in, and you will discover what the y value is. Sometimes I ask for it, so you might want to just do it, just to prepare yourself for that. But sometimes I don't. All right. It's pretty obvious. If there are 2 blanks to fill in, then I'm asking for both the x and the y. If there's just one blank to fill in, then I'm really only asking for the x. The other way to tell is to look for the keyword at. If I want the y values, I would say of or is. Yeah. So if I say there is a maximum of, well, then I'm asking for the y value. Or if I say the maximum is, then I'm asking for the y value. If I just say at, then I'm only asking for the x value. So of is y, at x. All right, we got a couple more. That's it for the polynomials. So I kind of started low and went high. with polynomials. Now I'm going to dive into rational functions. Rational functions have denominators. It's called a rational function. So notice the domain is negative infinity to -1 union -1 to infinity. In other words, x plus 1 cannot be 0 because you can't divide by 0. That's one of those domain rules. So since x plus 1 cannot be 0, -1 has been excluded from the domain. So we have now a difference between partition numbers or partition values and critical values. All right. So -1 is a partition value, but it's not going to be called a critical value. Because it's not in the domain. Critical values must be in the domain. All right, let's find the rest of the partition values. So f prime of x. Quotient rule. It's been a while since we did a quotient rule. Derivative of the top, 2x plus 5, times the bottom, x plus 1, minus the bottom, the derivative of the bottom, 1, derivative of the bottom is 1, times the top, x squared plus 5x plus 6, all over the denominator squared. That's going to be 2x squared plus 5x plus 2x plus 5 minus x squared minus 5x minus 6. That's just the top. All right. And then we're going to set it equal to 0. All right. Normally I put the 0 on the right side. So let's go ahead and do that. I got 2x squared and -x squared. I've got 5x, -5x cancel. 2x, and then I've got 5 and -6 is -1, and I set it equal to 0. You can put the 0 on the left if you like, but I normally put it on the right-hand side. All right, let's try to factor this. X times x, 1 times 1. The signs are all messed up. Look, if they're both negative, then you won't get a -1. If they're both positive, you won't get a -1. Remember, the last term is a product of these factors. So you're multiplying these to get this last term here. So they can't both be positive and they can't both be negative. So that means one of them has to be negative and the other one has to be positive. Well, that's not going to work either. Why not? Well, because if one of them's negative and one of them's positive, then the middle terms would cancel out and you wouldn't have this 2x in the middle. So I'm giving up. It's not factorable. And the sooner you discover that, the sooner you don't have to waste a bunch of time solving it. Or trying to solve something without having another technique. there are lots of different techniques for solving a quadratic equation. I'm going to write this down so I don't lose it. Partition numbers. Sometimes I call them partition values because they are values of x. I don't know what the rest of them are. I only have one of them so far. These other ones are going to come from solving this equation. I also don't want to forget my derivative. My derivative is this, x squared plus 2x minus 1. But don't forget the bottom, x plus 1 squared. All right. When you're solving the derivative to find the critical values, you can ignore the denominator. That's fine. But it's not going away. It's still there. You're just ignoring it while you're solving for the critical values. Now you can erase all this stuff. And you're going to solve the numerator by using another method. You can use the quadratic formula, or you can do something I teach in my college algebra class called completing the square. That's where you move the -1 to the other side. You make it +1. Then you add +1 to both sides. That makes the right-hand side equal to 2. You're basically making the left-hand side a perfect square by moving what was causing the problem, right? Because the problem is that last term is negative. So I say, okay, if you're negative, I'm going to move you to the other side. You'll be positive, and now I'll be able to factor this out. And you're going to get an irrational number. I'm going to need to grab my calculator to calculate what this is. It's going to be plus or minus the square root of 2. So on my calculator, I've got the square root of 2, 1.41. So x is going to be -1 plus 1.41 or -1 minus 1.41. I'm just moving the negative +1 to the other side and making it -1. I don't even need to use a calculator for that. It's going to be 0.4 or -2.4. For graphing problems, you can round to the nearest tenth. There's no standard. Some people do hundredths. I usually only do hundredths for the business apps because of money. Everything else, I just do tenths. There are some problems we've seen where we round to the nearest whole number. This one probably wouldn't be very good to round to a nearest whole, right? So I'm going to go with tenths. All right. So those are our other two partition numbers. -1, 0.4, and -2.4. Okay. So those are the partition numbers. The criticals are just the two that we got from solving the quadratic equation here. Those are the criticals, CVs. That's really just vocabulary. All right. I want you to know that sometimes these are the same. Critical values and partition numbers are the same. If the domain is all real numbers, then they're the same. But if the domain's not all real numbers, well, then there's usually at least one number that's in the partition, but it's not considered critical. So now we're going to do our test. So this is what we're going to test here. There's several other ways to solve for these decimals. You could have put them into a computer solving program. Some calculators have solving apps. Phone might have a solving app. Or there's always the original app. It's been around for hundreds of years called the Quadratic Formula. You've seen me use it a couple times. I try to avoid it if I can get away with it. But I wanted to just show you every technique that I could think of, and maybe even ones I haven't thought of too. It's hard to show you something I haven't thought of, but maybe it'll come to me in a dream or something. All right, so we're going to test this thing. And we're going to make our bins. Now watch how I do this. Negative 2.4, that's a critical number. That gets a solid line. All right. Negative 1, I put a circle around it because it's not critical. Why is that important? Well, because there cannot be a point if it's not critical. Only critical numbers can be points on the graph. In other words, maximums, minimums, those are points. This cannot be a point. So I have to have some way of knowing that if it does go plus minus or minus plus or something, that my brain goes, but wait a minute, that's not a point. So it's almost like you're treating these two sets separately. In fact, you are treating them separately. So there are 4 bins, but this bin and this bin do not overlap with each other in any way. All right, so now pick your test values. How about 1, 0, negative 2, and negative 3. And plug them all into here. You might want to do some scratch. All right, let's start with 1. So I got 1 squared plus 2 times 1 minus 1 over 1 plus 1 squared. Now all I care about is whether it's positive or negative. Positive. Once I'm sure, I'll put it in black to be sure of it. Right? 1 squared is 1, plus 2 is 3, minus 1 is 2. That's positive. 1 plus 1 is 2, squared is positive. So positive divided by positive is positive. All right, let's go on to the next one. 0 squared, 2 times 0, 0 plus 1. So 0 squared is 0, 2 times 0 is 0, minus 1 is negative. Negative divided by a positive is negative. So this one's negative. Partition number, it's an asymptote. So I skip it over to the next one, negative 2. Negative 2 squared, 2 times negative 2, negative 2 plus 1 squared. Negative 2 squared is 4. 2 times negative 2 is negative 4. That's 4 and negative 4, which is 0. 0 minus 1 is negative. Negative 2 plus 1 is negative 1, but then I'm squaring it. So it's positive. So that one's negative. All right. And then finally, my last one, negative 3. If you want to take a bet, I bet you it's positive. Let's see. Want to bet? Let's see. Negative 3 squared is 9. 2 times negative 3 is negative 6. So it's 9 plus negative 6, which is 3. 3 minus 1 is positive. And then negative 3 plus 1 is -2. Squared is positive. So that's positive, just like I said here. So that's it. So I've got increasing, decreasing. So that's a max. This cannot be anything. Decreasing, increasing. So that's a min. And this is non-critical point. It's not even a point. All right. It's an asymptote. It's a partition number. It divides up the plane into different areas, but it has no point there. So my final answer is increasing, negative infinity to negative 2.4, union 0.4 to infinity, decreasing, negative 2.4 to negative 1, union negative 1 to 0.4. Now I should point something out. If this was a critical point, right, if it was part of the critical values, then this would be a solid line. I would call it a critical point, and then I wouldn't have to jump over it with the union. I would just go negative 2.4 all the way to 0.4, and this point would be included as a value in the graph. But because it's a partition number, it's separated, and so that value -1 is not actually included in the answer. It has an open parenthesis, which means that point is not actually there. Okay. Now these ones are separated clearly by space. So we have a union, the different types of unions. This is a union that's because they're completely separated by space. These ones are actually touching each other, but there's an asymptote between them. So they're getting super close. I shouldn't say they're touching. I mean that the regions are touching, but there's a dotted line separating the two. All right, for this one, I actually want you to find the max and the min. So a max, or a local max of blank at -2.4, a local min of blank at 0.4. And now you have to go back to the original function. The original function was x squared plus 5x plus 6 over x plus 1. So we're going to do 2.4 and 4. Oh, God. Just do it on your calculator. 2.4 negative squared. Negative 2.4. Oh, negative 4 point. Oh, it's negative squared. Sorry. So it's a 4.345. Negative 2.4 times 5. Oh, that's 12 plus 6 plus 4.345. Negative 1.655 divided by negative 2.4 plus 1 is negative 1.4. And so that's 1.2. It's actually 1.18, but I'm rounding to the nearest tenth. I rounded that to 1.2. So that was this one. Let's do this one now. So 0.4 0.4, 0.4, 0.4 squared is 0.16 plus 2 plus 6 over 1.4. So that's going to be 8. I should have done that one first. Oh, it doesn't really matter. That's going to be 8.16. See why I don't do this on every problem? Divided by 1.4 is 5.82. So I'll take 5.8. So again, if I say max of or max is or minimum of or minimum is, then I want you to go through all this work to plug in these numbers to find what the maximum and minimums are. I'd say I probably asked that maybe on half of them, not on all of them. Okay, so I think I got time for one more. It's under one of these rational functions. So we got 6x squared plus 30x plus 47 all over x squared plus 5x minus 6. All right, so put the dog out before he starts barking at me on my last problem. So, okay, so we got another rational function. Now again, rational functions, you want to look for the domain and then find the partition numbers. So the partition numbers include numbers that are not part of the domain. All right. So we're going to set the denominator. You only do this for rational functions. Equal to 0. Or you could set it not equal to 0. It means the same thing. Again, it's semantics. You're saying that these values are not part of the domain. So because they're not part of the domain, they are partition values. So I want to find the partition values, so I'm just going to keep it as equal to. So I've got x times x. Let's try 2 and 3 to make 6. I've got that same issue we had last time. If they're both negative, then they don't make a negative 6. If one of them's negative and one of them's positive, then they don't make a 5, right? You want them to satisfy both criteria, right? They have to multiply to be a negative, but add to be a positive. So I'm going to have to do a positive 6 and a negative 1. Now, when I multiply them, I get negative 6. And then when I add them, I get positive 5. So my partition numbers are negative 6 and positive 1. Remember, when you solve an equation, you're finding the numbers that cause the factors to be 0. So this is x plus 6, so it's negative 6. X minus 1 becomes positive 1. So far, my partition numbers or values are x equals negative 6, 1, and then I don't know. I don't know how many more I'm going to get. So now I have to take a derivative. Two dogs. I had to let the other dog out. Now I have to take a derivative. So that very beginning is only for rational functions. Set the denominator equal to 0 and tell me what the partition numbers are. And again, I don't need to be repetitive, but it is kind of my job to be repetitive. The partition numbers are equal to these, but the domain is x is not equal to these. So these are numbers that are not allowed in the domain. All right. I'm not asking for the domain, but you should have a good understanding of what domain is. I have asked for it before. Just not in this chapter. All right, so this is going to be rough. All right, so we got the quotient rule. The derivative of the top, that's 12x plus 30, times the bottom, x squared plus 5x minus 6, minus the derivative of the bottom, what's that? 2x plus 5. Keeps getting so dark in here. Derivative of the bottom times the top, 6x squared plus 30x plus 47, all over the denominator squared. Oh, man. It looks messy, huh? I remember in the previous, when we first learned this rule, I would have said, just type it in like this, and you don't need to worry about it. Unfortunately, those days are over. We do need to worry about it because we need to find the critical values. So let's see. Let's see if we can clean this up at all. Doesn't look too promising. Well, we got no other choice but just to start multiplying. So I've got 12x cubed. This is going to be messy. That's why it's the last example. The messiest one. 60x squared minus 72x. I'm going to show you a little trick. I'm going to put the tops and the bottoms like this, and watch where I put the bottoms. I'm going to put positive 30x squared, positive 150x, and then negative 180. So that's that. Now let's do this one. Tops, 12x cubed, $60x squared, 94x. Yeah, 2 times 40 is 80, and 14 is 94. And then here's the bottoms. 30x squared, 150x. You might notice a pattern here. And then, oh God, 5 times 47, 235. All right, I'm just going to ignore the bottom for a minute. Let's clean up the top. So I've got 12x cubed plus 90x squared plus, oh no, my brain hurts. I've been going at this all day now. So much so it's getting dark out. I'm still working. 150 minus 72. I don't know what time you're watching this, but it was winter when I started, and now it's spring, just to give you a hint. Okay, and then I got this minus here, so it's going to be minus 12x cubed minus 90x squared minus what's that? 150 plus 94, 244x, and then minus 235. Now watch. We could have done this back in the previous not chapter, but I guess chapter, whatever. Whenever we learned the quotient rule, whatever chapter that was. Oh, it's been so long. But I didn't make you do it back then. And I think I said, well, someday you're going to have to do it. So today's that day. But it's not that bad. It's just a lot of busy work and bookkeeping. That's what we call this, bookkeeping. It's kind of boring. But it's very important to keep track of everything. The 90x squared, those are going to cancel. I think that's it. Oh, 12x cubed and negative 12x cubed. Those cancel. So altogether, I have 78x and negative 244x. So that's negative 166x. And then I've got negative 180 and negative 235. And that's it. So this is the numerator. And then this is the denominator. And I just sort of had the denominator on hold. I don't want to erase my f. I might need it later. My f prime now is negative 166x minus 415 over x squared plus 5x minus 6 squared. And now I need to find out if there are any other partition numbers. So I'm going to set the numerator equal to 0. I'm going to add 415 to the other side. Here, let me just show that step. Adding 415 to both sides. And then divide by 166, negative. Oh, and then round to 1 decimal if necessary. So 2.5. I didn't even have to round. It came out nice, 2.5. All right. Oh. Well, 2.5 is exact. Yeah. Or you could write it as a fraction. What's that? 5 halves. I don't care. Either one. They're both exact. If this decimal went on and on and on and on and on and on, then it would not be exact. Then I would prefer 5 halves. But it doesn't. So when you're dividing by 2, it comes out nicely. If you're dividing by 3 or by 6 or by 9, it's not so nice. All right, so we have one more partition value. Oh, it's negative, by the way. Shit. Almost screwed that up. Negative 5 halves. So those are your partition numbers, or partition values. All right, so now let's do our sign test. I got negative 6, negative 5 halves, and 1. Remember, these guys are not critical. This one is critical. So this one's solid. These ones are dotted. All right. So the only one that's critical is 5 halves. Only one critical value, negative 5 halves. Keep forgetting to say negative. All right, so now we're going to test. I need to pick some test values. So how about 2, 0, right, in between there, 0, negative 3, and negative 7. Again, you get to pick any numbers that you like, as long as they're in the appropriate bin. All right, this is going to be tough. This is going to be a lot of work. So let me make some space right here for testing. All right, let's start with -7. Let's start with that one. -7. Plug it into here. If you want to have a calculator handy, you can. Now, I will mention something. Here's something you can do to save some time. The denominator is always positive. Yeah. The denominator is never going to be negative because it's being squared. Right? The denominator of the original function didn't have the parentheses around it, so that's a whole different story. But the derivative is being squared, so it's always positive. So when I do my sign test, I don't really have to plug anything into the bottom. I can just skip it. Whatever happens on the top is going to determine the result of all the bins. So because these numbers are rather large, I don't want to have to do mental math with big numbers. So let's just do it, using a calculator. So I've got -166 times -7. That's positive 1162. And then minus 415. I don't care about that number. I just care that it's positive. If you're impatient, you can guess. Maybe that's right. I don't know. You want to bet? I don't know. I don't know. I don't want to bet. I want to test. So let's go to the next one. -3. So I got 166 times -3. That's 498 minus 415. It's still positive. I'm glad I didn't bet. Hey, maybe both of these are negative. I don't know, maybe there's a pattern here. Let's try 0. You don't even need the calculator for 0. When you plug in 0, you get 0 and then minus 415. That's negative. Check. Let's do 2. So -166 times 2. And then minus 415. That's negative. So you see what I mean about the pattern? It doesn't always alternate plus, minus, plus, minus. That's the most likely bet, but I wouldn't bet. I would test, right? I mean, if you want to bet, you could bet yourself and then test and see if you win or not. I would have lost this bet. So this one's plus, plus, minus, minus. So this is increasing, increasing, decreasing, decreasing. These guys are not critical. That's why I put the dotted lines. But this one is critical, and so that's going to be a max at that value. So I've got increasing from -infinity to -6, union -6 to -5/2, decreasing -5/2 to 1, union 1 to infinity. And again, if these were solid lines, then these would be critical values. And then this would go -infinity all the way to -5/2, and I wouldn't even mention the number in the middle, right? Because the sign doesn't change. But because it's a non-critical value, that's why it's so important to know the difference between the partition numbers and the critical numbers. Because when you do the test, you're treating them differently. Right? We didn't just give them those names because we thought it would be cool to make you memorize more names. Those names help you deduce the results of the test. Right? If you apply the results differently based on what category those numbers are in. Okay, and then the hardest part of this whole problem, not the hardest, but it's certainly the most tedious, is plugging in this number into this function to figure out what the maximum value is. So I I guess I'll do that now. The max is at -5/2, but I have to plug it in. I'm going to just switch to a decimal. To plug it into this function here, the original function, which I've been hanging on to this whole time. So I've got 2.5, -2.5 squared, 6.25, oh, then times 6. So that's 37.5. And then I've got 30 times -2.5. So that's going to be -75 plus 47. And then on the bottom, I've got 2.5 squared, which is 6.25. 5 times 2.5, negative. So that'll be -12.5 minus 6. So then just go across. I got 37.5 minus 75 plus 47. It's 9.5 in the numerator. Again, this is just, accounting here. 6.25 minus 12.5 minus 6. -12.25. So I've got 9.5 divided by -12.25. Which is -0.8. -0.8. Huh. That's interesting. I was hoping for a better number than that. Let me double check my math. 37.5 minus 75 plus 47. Yep, 9.5. And then 6.25 minus 12.5 minus 6. 12.25, yeah. 0.8. All right, so I have a max, a relative max, or a local max. Of -0.8 occurring at x equals -2.5. I sure hope I didn't make a mistake because it's been a long day and a lot of filming, but I hope I'm done. If you find a mistake, please email me, let me know. I'll try and compensate for it one way or another. I'm a little skeptical about this number. When I did it off camera, it was a slightly different version of this problem. The answer wasn't so bad. It came out nicely, kind of like the 5/2 came out nicely. I'm trying to think, but I can't think on camera whether or not I could have done it more elegantly and gotten a nicer value. I mean, I guess I could do something weird like this. I could say 950. Oh, I don't know why I'm doing this on camera. Over 1225. So let's divide that by 25. That's 38. I'm just moving the decimals over and trying to get a nicer answer. 1225 divided by 25 is 49. Is 38 divisible by 7? No. So 38/49 would be the exact value. 38/49. You could actually, I just did that to show you that the decimal is equivalent. Watch, 38 divided by 49. It's still 0.7755, which if we're rounding to one decimal is negative 0.8. So, well, now I feel like it was, I'm confident now, so it's definitely not wrong. Well, I hope you all enjoyed this experience and this dive into the first derivative test. Next time, we'll learn the second derivative test. But until then, I'm Dr. Jordan, and I'll have to see you on the internet.